Let's roll. Start out with, are there any questions?
Do we have a final in this class?
There is the last test.
Does that cover everything or just the last couple chapters?
The last couple of chapters, explicitly.
Okay.
There's,
Yeah, well,
the word force might still be used. But
yeah. I just know if we have like here's chapter 1 part of the test, here's chapter 2 part of the test.
no,
Okay.
unless there's a groundswell for it, but no.
Will we have class the week of Thanksgiving?
Yes. Because I think the Thanksgiving break starts Wednesday.
Mm-hmm.
And for some of you, it's a great excuse to get away from the family. Any other questions? All right, I want to start out, and before we start talking about black holes, there was a problem from the textbook that students have had issues with in the past. I just wanted to run through it. And, oh, there we go, problem 43. Many people mistakenly believe that astronauts who orbit the Earth are, quote, above the gravity, unquote. Calculate G for space shuttle territory, that's 200 kilometers above the Earth's surface. So we have Earth, 200 kilometers, or 200,000 meters, or 2 times 10 to the 5th meters. And okay. So we're trying to find little g here. Because remember, we can find gravitational force 2 different ways. There's mg, and then there's the big formula, gm, I guess that would be mass of the object, mass of the planet, mass of the object over r squared. And sort of, we're leading towards this at the end of class last time. So the mass of the object does not matter, which is true regardless of where you are. And so the formula is just basically big G times the mass of the planet times this R right here. So 6.67 times 10 to the negative 11th. Mass of the planet. In the problem, Hewitt uses 6 times 10 to the 24th. I think in class last week I did 5.99, 5.98. And what is R?
Radius.
Of?
The circle.
Okay. So 200,000?
No.
Why not?
It's half of it.
You were correct in no, that is not R. But what is R? You don't necessarily have to give me a number, just you can describe what it is.
The distance between the objects?
So 200,000?
Yes. Is that right?
Is it from the center of the object to the outer layer, or to the end?
Do the,
I don't know how to. The middle to the outer.
the middle of the object to the outer edge of the,
No. Oh, is that small dot the object?
yeah, that's the object right there.
Oh.
Oh.
That's the planet.
Oh, I thought the big one was the planet. Oh, not the planet, the object.
Planet. Object. Trying to go for some sense of scale there.
Is it like half of what it goes around? Is it circling the object, or is it just, we're just measuring in between? Actually, no, never mind, that was not a great question. It seems on the board, but never mind.
People have dancing around it, but no one's quite put it together in one sentence. Someone else wanna take a shot?
Is it between the object and the center of the planet?
Yeah, it's the center to center distance. So, you were right, Brianna, you said, I think the radius of the circle, or the orbit, yeah, that's true. Which would be from here to here. So it's 200,000 meters plus the radius of the planet. And the radius of the planet was 6.38 times 10 to the 6th meters. That's 63800 meters. And that's given in the problem. And so we would tack on 200,000 to it, so on the denominator we have we got 200,000, we get 6,580 squared. Someone be kind enough to do a calculator on that one. Do a calculator, use a calculator.
I just wonder if we're going over like a problem.
Yeah, from chapter 9, problem 43. No one asked for it, and I just thought I'd volunteer it.
Well, we never listed it.
No?
Oh.
And what will the units be?
Meters?
Stopping there? Or are you just giving someone else a chance to finish?
Giving someone else a chance.
All right, so we got meters down, so let's keep going.
Meters over R squared.
No, not. So if we're looking at units here, the units of this are Newton meter squared per kilogram squared. Units of that are kilograms. And the units of that is meters squared, because we're squaring it. What does that simplify into? That's a different way of looking at it. Or you could try to think of what exactly did we find?
Is it going to be meters per second squared?
Yes, it is.
I think we can.
We were finding little g here, 9.8 meters per second squared near the surface of the Earth. Thank you. But when you're 200,000 meters up, 200 kilometers up, it hasn't changed a whole lot.
How do you actually get meters per second squared from that?
From all that. It has to go, part of it is, well, let's get rid of what we can. So, so that meter squared cancels out with that meter squared. And that kilogram will cancel out with one of those. So what we're left with is a Newton per kilogram, just which a Newton by definition is a kilogram meter per second squared. Sorry, meter per second squared divided by kilograms, and they cancel out. That's how you can get there from there.
Can we, once we have enough of, the ends, like the meters per second squared, can we go over, like we did before, on it, like when we did acceleration equals, meters over second squared?
Sorry, I'm not quite sure I followed what you're asking.
Can we, once we have all of the, chapter done, can we go over how do I phrase this? You know how we know how, velocity equals,
Oh,
yeah,
as in this quantity here at the units?
yes, yes.
Ah.
Standard units, that's what it's called, right?
Yeah, okay.
Can we go over that?
Yeah, no problem. I'm trying to think of what is different here, because we're dealing with, in this particular chapter, primarily we are dealing with, big G is the newest thing. We have mass, R is a distance. Obviously, in this problem right here, we're dealing with acceleration. I think there's something else in this chapter that is relatively new. I guess weight, and I think those are pretty much the quantities that we're working with in this particular chapter. So that's a force and that's a force. Weight and just the generalized force due to gravity. So what are the standard units of force?
Newton?
Yep. So we would write that. Oh, thank you. Mass, what's the standard unit of mass?
Kilograms?
Absolutely. Standard unit of acceleration?
Meters per second squared.
Although newtons per kilogram, as shown here, and as we did earlier, this in a month ago or so, Newton per kilogram also is valid, although meters per second squared is usually what's used. The unit of distance that keeps showing up in the bottom of these formulas.
Meter.
And then G is the new one. And if you get sort of confused about what that is, since it is a constant and it'll be given to you, you can always just look at the first page or top of the quiz or top of, you can look it up. However, it's written over there. Newton meter squared per kilogram squared. And these units are set up so that everything will cancel out but newtons when you're using the full formula. Because you'll have two masses here, so that's 2 kilograms, or kilograms squared. So that's gonna cancel out with that kilogram squared. And then you've got meter squared on the bottom, which will cancel out with that meter squared, and you're left with newtons. So is that the kind of thing you were wanting?
Yes.
Okay.
And then anytime it involves energy is when we put the jerk in.
Joule.
Joule, sorry, not jerk.
Jerk's a different thing.
Yeah.
Yep, and we're about to do some energy stuff.
Was that quiz, the 6 and 7, was it together when you had it originally the other week, like in one?
Yeah, I had front and back.
She had it, I went this morning, I have to go back again to take 7, because she wouldn't let me take both of them. Cause it was like 2 separate ones, so I took 6 this morning, but
This is,
I guess you need like 2 different HL codes to do 2 separate.
yeah, and there's a disconnect between me and the process that they go through, so I need to, I'm
Oh, no,
not quite
it's
sure
okay.
why it's as confusing as it is, but I'm not running it. I imagine
Yeah.
they're dealing with a lot of scenarios I don't even think about.
I don't know, she's in there on FaceTime with like her, it looks like her daughter, I don't even know how, like.
Okay,
Yeah.
All right. thanks for letting me know. All right, any questions on this problem specifically, or any of the things that it might have spawned in your head? That's just doesn't seem to be going right today. All right, so I'm gonna keep the planet there. Now, there's gonna be a certain amount of derivation that I'm about to do, and yes, I know as excited as you are seeing letters all over the board, the primary purpose, there's some conceptual things that definitely are within scope. So what I'm gonna do is I'm gonna launch an object from this planet. Launch. Object. Mass of the object is m sub O, and then we have a planet here with some mass m sub E. And I want to launch this object so it will not come back. Because typically, I throw an object up in the air, it comes back down. I throw it harder, it'll go farther up in the air, and then it'll come back down. It takes longer and longer for it to come back down. There is a speed, though, at which it will leave the planet and never return. We are assuming object does not hit anything. This includes air. I'm not worried about air resistance. I'm not launching it. It's not gonna hit a satellite. It's not gonna hit another planet or moon. In this nice little ideal universe, we have a planet and an object that we're launching. We are assuming object's initial speed is the speed, I'll just use shorthand, just after launch. I am not worried about it. If I have an object and I'm throwing it up into the air, for instance, the marker, if I'm trying to sling the marker off the planet, I'm not worried about the fact that it's starting at rest. All I care about is the point at which it leaves my hand. Or in this case, I worry about it at the point when the object has left whatever is launching it. Now, we can't use Newton's laws easily here because the force that the planet exerts on the object is not particularly constant. Now, if I'm dropping a marker, or if I'm throwing the marker in the air, it's not leaving the planet far enough. I can get away with mg, where g is close enough to a constant. But g is not close enough to a constant here, little g. The acceleration is not close to a constant. So when it's here, and suddenly it is expanded. So when the object is here, what are all the forces acting on it?
Its mass.
Another force?
I don't know.
Somebody just said it.
Weight.
Except since we're in outer space, we go for the more generalized term, force due to gravity.
Mass.
So, and which way is it acting? Well, towards the planet. Is this a conservative force or a non-conservative force?
Conservative.
Say it with confidence.
Conservative?
Okay. Yes, it is. I was hoping for more confidence. You seemed more confident the first time than the second time.
I'm sorry.
What the heck? Third time, with confidence.
Conservative.
Yeah, there we go. What does that mean in terms of energy?
It keeps it the same.
Yeah. Or conserved. So, whatever energy it has at this point, it's going to be the same energy throughout the entire trip. What are my two kinds of energy?
Kinetic and potential.
Like you mean it.
Kinetic and potential. I wasn't sure about the second one. This one.
So we have some initial kinetic plus some initial potential is equal to some final kinetic plus some final potential. Just the shorthand notation. We have a certain amount of kinetic, we have a certain amount of potential, whatever that adds up to in the beginning, that's what I have throughout. All right, it's about time for that unison thing. I'm about to ask you that question that all of you should know the answer to without my doing prep or giving you a chance to look it up. However, you do have a chance to look it up. Because I am gonna ask you what the formula for kinetic energy is, and you are all gonna know it. And sing it, in it like a chorus of angels. It's gonna be good. Here we go. What's the formula for kinetic energy?
One
Half
mv squared.
Wow, that was not the chorus I was hoping for. Or my imagination of angels is just way off. I'd like to hear that one more time. That's what we're going for. Should have it memorized.
But just for clarification, it will be up top of the test, right, or no?
It probably will be written, but I shouldn't have to write it.
Okay, good, just in case.
All right, so what's the formula for kinetic energy?
1/2 mv squared.
That was better definitely, but still felt like there were a couple of gaps in the room. Anyway, all right, so we have 1/2 mass times the speed squared, initial. Now this mass here is the mass of the object, so put a little 0 there, or O for object. Now we have this potential energy, the gravitational potential energy, the one associated with the general formula. MGH is not appropriate here, because MGH is only appropriate if G is relatively constant. The little g is relatively constant. So this one, I'm not going to derive it for you. I'm just going to sort of say this is what the formula is. Deriving it requires calculus. So it's minus or plus negative big G mass 1, or mass of the object, mass of the